Yes, sir.
So last day we have seen this bending stress in beams, and finally we came up with this expression where the stress of a layer is related to the distance of that layer from that neutral layer. Okay, so let me quickly draw the part. So sigma was equals to E by R into Y. This was the expression we have found out in the last class, where E is the Young's modulus of the material, R is the radius of curvature of the neutral layer, Y is the distance of the layer from the neutral layer, and the sigma is the stress in that layer, which is Y distance away. Now, if we want to see from a so whatever we have seen from this aspect, right? So from this side, if this is say our eye is like this, so if you are looking from the side of this beam, then we talked about this element which is combined by or which is disconnected by two transverse sections, and after bending they are meeting at some point. So whatever expression we have derived from this part, we have seen it from this side. Another way of looking of the beam is if we want to see it from this side. So in this, if we see from this section, this side, we can only see a beam section here. Okay, so we can only see, suppose this beam is of rectangular section, so we can only see a plain rectangular portion. If we want to see that section, is known as a beam section. This is nothing but one of the transverse sections. So if that part is here, say we are looking from that section, this is the central line of the this portion, so this is called a beam section. Say it is the width is B, depth is D. Now this say this parts or this layer is called as NA or neutral axis. So neutral axis is basically neutral axis of a transverse section is of a beam is basically the line of interaction of the neutral layer with the transverse section. So neutral layer was looking for, we can see if we want to see from this side, we are getting the neutral layer, and then when it is intersected with the transverse section, it bisects the transverse section by some axis. This axis is known as neutral axis or NA. Suppose we can now consider a elemental area here, say dA, which is y distance away from this neutral axis. Okay, so what is the stress in this elemental area? So stress in this elemental area is E by R into Y, as it is Y distance away from the neutral axis. Now, what will be the force in this case? The force will in that elemental area will be, if it is sigma, so sigma into dA, that means E by R into Y into dA. So this is the force on the elemental area. Only this area now we are talking about. So whatever stresses is E by R into Y, and if we multiply the stress in the elemental area dA, we can get that force acting on this elemental area. Now if we want to get the total force on the entire beam section, so we have to do an integration over the entire depth of this beam. So total force on the beam section is E by R. So integration of E by R into Y dA. This portion of this expression is constant, as E is always remains constant for that material, and R is the radius of curvature of the neutral layer. So we can keep this part out of the integration. So the remaining part will remain integration of Y dA. Now for pure bending case, no force is acting on this beam section. So no force is acting on the beam section. That means the total force which we have determined or estimated on the beam section will be 0. So E by R integration of Y dA will be 0. Now this part again, it's a E value, Young's modulus of a material can't be 0, radius of curvature can't be 0. So this portion is not 0. So only portion left is integration of Y dA is equals to 0. Do we know this expression in this course? Have we come across this sort of expression, integration of Y dA, where Y is the distance of area from any axis?
Area moment of inertia.
Area moment of inertia. Is it the right term?
So why
No,
zero उत्तर?
that's not the
Please और एक बार बोलो.
Second moment of inertia.
Second moment of inertia. Second moment of
first
inertia.
moment of inertia.
First of all, that is called second moment of area or moment of inertia. But that is not that integration of Y squared dA.
Yes, sir. Y square dA.
So
Yes,
what
sir,
is
yes,
this?
sir.
Is it fast moment of is this the fast moment of any area? Why we do the centroidal calculation, then we do this sort of expression, right? Integration of Y dA. So this is basically the moment of area of an axis. The moment of area of an axis becomes 0 only when that axis is coinciding with the centroidal axis of the section. Now from this expression it is coming us that this moment of area or this of this section is 0. That means this now the section, the neutral axis, has to pass through the centroidal axis. Only then the total expression, whatever I have written, is valid. So neutral axis or NA is basically the centroidal axis of a section. So say this is a section here, beam section we can say. If we know the centroidal axis of this beam section, that is nothing but our neutral axis of this beam section. Okay. Now, if we want to see that how much moments is acting, so before that I want to say one thing. So this is, we are seeing from this part of the beam, and this is the, we are looking from this part of the beam. So from here, this was the case which we have done, that in the, this was the neutral layer, upside it was the reduction of the length, and bottom side it was the increment of the length of the layer. So when there is some decrement or decrease, we can say that, and due to the change in the dimension of the length of the layer, some stresses are getting generated. From our very first chapter after mid-sem, we know that when the length decreases or when the dimension changes and there is a decrease in the dimension, compressive stresses are getting generated, and when there is some increase in the dimension, tensile stress gets generated, and that's what have been shown here. So why we have seen like this, why we don't have seen the for the entire thing? So what was the stress expression? E by R into Y. Now what was Y? This is the neutral axis. This is the layer, say. So Y. So what if Y is 0? What will be the value of the stress? If this Y is 0, what will be the value of the stress? We can also see from the expression, no? This is a
Zero.
constant. Yes, this is a
Zero.
constant part. So this will remain constant from the entire beam section, whatever we are considering for that moment. Y and sigma are the variables. If Y is 0, sigma becomes 0. Y, and when we can say the Y becomes 0? When this Y will become 0, here we can see from it here. When the Y will be 0? What is the distance Y?
When it will coincide with neutral axis.
Yes, good. So because Y is the distance from the neutral axis. When the distance coincides with the neutral axis, that means Y is 0. And when Y is 0, we just have seen that sigma is 0. That means stress at neutral axis is 0. Stress at neutral axis is basically 0. That's what happens.
एक्सक्यूज मी सर, आवाज नहीं आ रही आपकी।
सर स्क्रीन फ्रीज होगी।
why the stresses at this top layer and bottom layers are maximum?
सर
Yes.
सर आपकी
Screen
स्क्रीन
share
शेयर है।
Okay.
आवाज चली गई।
Okay, just 1 minute. Is it fine now?
Yes, sir.
Yes, sir.
Okay. So what I was asking that why the stresses were maximum at the top layer and at the bottom layer? At least from this picture, the maximum values are at the top layer and at the bottom layer. Why is so?
Because of y.
Yes, because y becomes the maximum at the top layer and also y becomes the maximum at the bottom layer. And as the y becomes maximum, from simple calculation, we can see the sigma also becomes maximum at this when y is maximum, or sigma simply varies with y. So that's why these figures, whatever has been shown here, it varies from G. Yes. Can you please mute yourself? So here,
ये तो मुझे पता है। तो मुझे ना लाई दिया, मेरा मेरा
excuse me, can you please mute yourself?
इतने में पिटते।
So this is, so from neutral axis, it is varying from 0 to 1 maximum compressive stress, and from neutral axis, it is varying from 0 to maximum tensile stress. Now, this compressive stress will have, now this compressive stress are acting on this section for the above part, that means some sort of compressive force is acting also. Again, some sort of tensile stress are acting below the neutral axis. So some tensile force will also act on this below section. Now, what is the force on that value? So now again, if we go back to our this part, so till now we know that sigma is equals to E by R into Y. F of a layer, F on layer, F means force, okay, is E by R into Y into dA, because we are considering about this case where this is the elemental area and this is the y. So E by R into y into dA. Now if we want to see that how much moment of that force is acting, so moment of that force F about NA, or that is neutral axis, is E by R into Y into dA into Y, that is E by R Y squared dA. Now this is moment of the force F about NA, but this is only for of the layer, right? As this force is on the layer, so only this elemental layer when we are considering. So the moment of the force on the elemental layer about neutral axis is this. Again, if we want to see the total moment of force on the entire beam sections, so total moment on the beam section is integration of E by R y square dA, E by R, again for as it is a constant, we can keep it out of the integration. Y square dA, we know this portion. What is this?
Moment of inertia.
Moment of inertia of this section about neutral axis. So we can denote it as our I. So from here we can see M is equals to E by R into I, or M by I is equals to E by R. So whatever we have seen earlier, E by R is equals to what?
Y by R.
E by R is equals to
Sigma.
Sigma upon Y. Sigma by Y.
sigma y. So if this is 1 and this is 2, so from it we can write that M by I is equals to E by R is equals to sigma by y. So this is the final expression or the relationship between all different material properties or some sort of distance properties for a simple bending theory. Okay. One more terminology we want to learn, that is section modulus. Okay. So section modulus, it says, so we know that when, okay, first let me write down the expressions. E by R into Y, and also M by I is equal to E by R equal to sigma by Y. For Y max, what is the sigma value? We have just seen it is equals to sigma max. That is maximum stress happens for Y max, that is the maximum distance from the neutral axis. Now, section modulus can be defined as, section modulus means Z, can be defined as this I of the section or the moment of inertia of the section by the distance of the outermost layer from the neutral axis. Okay, so this is nothing but the moment of inertia. This is nothing but moment of inertia of a section about NA, and this is nothing but the distance of the outermost layer from neutral axis. Okay. So if Z is I by Y max, so if we want to modify this expression or rearrange, now this Y is maximum, and when the Y is maximum, sigma is also maximum. So, and when Y is the maximum, then I by Y max can be called as the section modulus or Z. So sigma M equals to sigma max into Z. This is another form of the expression where Z is the section modulus of the beam section, which is defined by I by Y max, and as the Y touches its maximum value, sigma will also be the maximum. So this expression can be modified as m equals to sigma max, sigma goes here, and this part becomes the section modulus Z. Okay. Now this m is, or whatever this moment we have found out, this is nothing but the moment of resistance of the section, and which is equals to the maximum bending moment. So m is moment of resistance of the section. This is coming from the stresses generated. So basically this is a resistance against the total load, and we know that the whatever the resistance generates from a section or from a material of the section is equals to the total applied load within the elastic limit. So when the m is denoted as the moment of resistance of the section due to the stresses generated, this m is also equals to the bending moment applied on the section. Which bending moment we are talking? So if this was the beam section, as we have seen in the earlier class, if this was the transverse section and this was the neutral layer, also this bending moment was acting here. So this moment is nothing but the bending moment applied on the section. Also it is called as the moment of resistance of the section. Why these two will become equal? Because this is the external moment applied. This is the resistance against that moment, which should be equal to the external bending moment as long as it is within elastic limit. So within elastic limit, this bending moment, whatever the bending moment will be applied, the moment of resistance will be equals to that bending moment values. Okay, so final expression, whatever we want to see from this chapter is m by I is equals to E by R is equals to sigma by Y. Second is sigma is equals to E by R into Y. All these are interrelated to each other. Z is I by Y max, and you can write down the expressions so that you can solve the numerical problem. And the final one is m is equals to sigma max into Z. So these are the expressions where basically all are coming from the main expression here. But if we want to know some small portions, we can use the expressions where this is Z is section modulus, I is moment of inertia about neutral axis, m is moment of resistance, which is also equals to the bending moment, and yeah, y is the distance of the layer, E Young's modulus, R is radius of curvature. So what is helping us? If we see the equation 4, what is helping us? For most of the cases, we don't know the value of moment of curvature. But if we know that how much stresses are getting generated, and if we can calculate the section modulus of that section, then we can find out that what is the maximum moment can be applied on that section. Okay, that's what this is the application of these expressions. Any doubt? Okay, so now we will do some simple problem first. So find out the section modulus of the rectangular section. Say this is B and this is D. What will be the section modulus for this rectangular section where height is D and width is B? I hope you have written down the expressions. So from here it will come up. How we should proceed?
NA.
NA. So what will be the NA for this rectangular section?
Through B by 2 and D by 2.
Yes, because it coincides with the centroidal axis. The centroidal axis for this section is just the mid section. That is D by 2 by, and also here it is D by 2. Very good. So this is our neutral axis. Now what we have to do? What is the I value here of the rectangular section about this neutral axis?
BD cube by 12.
BD cube by 12. Why you have considered BD cube by 12 and why not BD cube by 3? Yes.
Centroidal x-axis.
Centroidal x-axis, because if we are talking about any bottom section, then it would have been BD cube by 3. Very good. But as we are talking about the centroidal axis and as it is we are talking about the NA, so NA is BD cube by 12. What is Y max value?
D by 2.
D by 2. Very good. So what is the section modulus of this rectangular section?
BD square by 24.
BD cube by 12 and D by 2. How much it is coming?
BD square by
6.
BD square by 6, not 4. BD square by 6. Okay, good. So now if we want to see the section modulus of a circular section whose diameter is D. Now find out the section modulus. First, what we have to do, we know for this case, we know the centroidal axis is at the center, which is passing through the center. So what will be the I value?
pi d raised to the power 4 by 64.
Very good. Pi d to the power 4 by 64. What is y max?
D by 2.
D by 2. What is the sectional modulus then?
Pi d cube by 32.
Very good. So pi d cube by 32 is the section modulus for a circular section of diameter d. It's very simple. So it's okay. So just we have to find out the moment of inertia of the neutral axis. Neutral axis means central axis. So moment of inertia of the central axis, then the maximum distance, then we can say the section modulus for that particular type of section. Now we are slowly going into the application of this entire bending stress chapter. We know this sort of problem, right? Cantilever beam is acting where a say vertical load is acting at the free end, and say this is the beam is of 2 meter length. Now this beam is having a section. So the section is, say, this is 40 millimeter and this height is 60 millimeter. So basically, if we want to see from this side, this is the beam section 40 millimeter and here height is 60 millimeter. Length is 2 meter. Cantilever beam acted by a concentrated load at the free end. We want to know the stress at failure. So, what is the stress at failure? Stress at failure means the maximum stress it can reach beyond which it will fail down. Now, when the maximum stress will reach, from the expression, when the maximum stress will reach, this Z is the section modulus of the section, which is constant for the section because it depends on the dimensional properties, that is not changing. So this will remain constant. Now when sigma becomes maximum values, M will also become maximum values. So if we, either way, if we know the sigma value, maximum sigma stress which can reach, we can say that the maximum bending moment that will act on the beam section can be found out. Or in either way, if we know the maximum moment which is acting on the beam section, if we know that part, from there we can find out the what is the maximum stress of this beam section. So for this case, the stress at failure has been asked, means that we want to know the sigma max value. So we have to know the maximum bending moment for this beam and this combination of load, and we want to know the section modulus from the sectional properties. So what will be this sigma max value? Before that, tell me what is the maximum bending moment is happening from this beam loading combination, from this cantilever beam acted by 2 kilonewton load. What is the maximum bending moment?
Two thousand.
4 kilonewton per
2000.
meter.
Maximum bending moment. Will it be 2000? What is the maximum bending moment is happening here? Where it will happen? Maximum bending moment? A or B? Or somewhere between A, B?
So A.
A. And what will be the value?
So 4 kilonewton
4
meter.
kilonewton meter, because this is simply W into L. So maximum bending moment is 2000 Newton into 2 meter or 4000 Newton meter. Okay. Now, what is section modulus for this section?
Newton meter by sigma max.
No. Section modulus we can find out na from the sectional properties. The section properties are here na. All the dimensions given. The height is 60 millimeter.
Yes,
Width is 40 millimeter. So from that, like that, we have just now done na this case. So that case I was asking that what is the section modulus for the rectangular beam section?
$24,000.
Good. So how he has done, she has done, see, this is basically 40 into 60 square by 6. Just now we have seen that BD square by 6. So BD square by 6, it will be equals to 24,000. What will be the unit?
Millimeter cube.
Millimeter cube. Okay. Now, so what is left? Only sigma max value is left. So now you can tell me what is the sigma max value.
One 1.6 into 10 to the power 8.
126 into 10 to the power 8. No.
1.6. 1.6.
Into 10 to the power 8. No. Sigma max. What is the unit you have considered?
Meter.
Okay. If it is millimeter, how much it is coming? Acha, 1.6. Okay, I think you are right. You have done it in meter. Okay. Let me just check it here. So this is basically, the aim is nothing but 4 into 10 to the power 6, because this is Newton meter. So 4 into 10, 6 into Newton to millimeter. And here the Z is 24,000 millimeter cube. So it is coming 166.67 Newton per millimeter square. Have you done just like this? I think this millimeter cube 10 to the power 6. I think, yeah, you are right. 10 to the power 8 is coming. Yeah. Okay. So this is the stress at failure at the maximum stress happening in the section. Okay. So just we have calculated the maximum bending moment, and we have also find out the section modulus for this rectangular section. Then we have just divided it and we have found out the maximum stress values or stress at failure. Now, yeah, so I think this is already there. Just 1 minute. Yeah. This is actually, so you can just write down the problem. So a rectangular beam where the depth is 200 millimeter, width is 300 millimeter. It is simply supported over a span of 8 meters. What uniformly distributed load per meter of the beam may carry if the bending stress is not to exceed, so maximum bending stress is given to us, we have to find out the uniformly distributed load per meter, that is a W we used to see, that W we want to calculate.
$45 kilonewton.
First of all, the unit should it be in kilonewton? Means or it would be something different unit. Uniformly distributed load per meter of the beam. So either it will be kilonewton per meter or newton per meter. So that unit should come. Okay. First of all, second is that the value is wrong. So I think or एक बार check कर लो. What is the, so what the things we do not know? First of all, what the things we know here? So D we know 200 millimeter. B we know 300 millimeter. Acha, length we know 8 meter. Sigma max we know 120 Newton per millimeter square. Okay. So what are the things we need to calculate?
Z.
How much it will be?
3 into 10 to the power 6. Nine.
B into D square by 6. No? No.
2 into 10 raised to power.
2 into 10 to the power
What is the moment? No, I am asking for the expression. If say, okay, let me do it in this way. So this is
Sigma max into Z. Sigma max into Z.
No. Okay,
Sir.
those things are fine. Sigma max by Z, but see here we want to know the W. So the bending moment we need to know what I am connecting. So this, first of all, this is a simply supported beam. Okay. So simply supported beam looks like this. This is and what is the load? Load is uniformly distributed load. uniformly distributed load. If this is W Newton per meter of this beam, if this is L, the entire length of the beam, what was the maximum bending moment? What is the maximum bending?
WL square by 8.
Yes, yes, that's what I was asking. So WL square by 8. That is the expression of this maximum bending moment. We have already done it. So for a simply supported beam, if the load is uniformly distributed load of W, this is WL square by 8. Now, do we know this L? Yes, we know that is 8. Okay. So 8 square by 8, basically 8W. So this AM is 8W. And yes, now as you were talking about, so another way we can find out the moment. So what will be the another way, or the ultimate value of the M max?
Sigma max into Z.
Sigma max by Z. Now it's very good. So what will be the value?
2.4 into 10 to the power 8.
Okay. 2.4 into 10 to the power 8. Always say unit. Unit is very important.
Mm.
Newton mm. Newton mm.
Newton mm. So now what will be the value of W?
Three into 10 to the power 8.
Okay, I think for your convenience, you can use the higher orders of the unit. Otherwise, it will be you will mistake any zeros, and then it will be difficult. So, can we just do it in Newton per millimeter, or say kilonewton per meter? Can we do it either Newton per meter or kilonewton per meter?
Thirty kilonewton meter.
Yes, 30
30
kilonewton
kilonewton per meter.
Yeah, that is one way of writing. This is easier to write it down. Your answer is also correct. No marks will be deducted for those cases, but it will be easier for you only to write down in this sort of. So this is the uniformly distributed load per meter of the beam. So the very first answer which she gave that 45 Newton. So now you understood where the unit will be very important, and here it will be Newton per meter or kilonewton per meter.
सर पर मीटर नहीं है
हाँ, per meter है ना?
वेट में सर
This is not weight. This is not weight.
यस
This
सर
is the uniformly distributed load.
यस सर यस
You remember that part we used to do that this sort of thing? Huh? So that W area and all those things we used to do, no? Remember?
यस सर यस
Yeah. So this is not weight. This is the external load, and this is running over the entire beam length. So and the intensity is load per meter length. So Newton per meter is the W. It's the intensity of this UDL loading. Okay. So that's why our unit should be Newton per meter, or force per meter length, or force per length. Anything is fine. Newton per meter, Newton per millimeter, kilonewton per meter. Anything is fine, which is more convenient to, you can use that. But unit should be like this, and this is the way of doing. So basically, this shows the connection between the two chapters. So from the last chapter, when we have drawn the shear force diagram bending moment, we used to draw the maximum bending moment, which is nothing but WL square by 8. And this is slowly we are going into the design aspects here. So with this maximum bending moment, what is the section values, and from there we can find out what is the load to be acting on the beam when we need to calculate the maximum bending moment. Okay, so is this fine? Then
सर excuse me
Yes.
सर
yes,
वो mx एक बार explain कर दीजिए WL square by 8.
W square by 8.
Yes,
Okay. Do you have written already that part? You, acha, let me just do it here. Where it is? Just 1 minute. Okay. So this is the simply supported beam. So just draw the shear force diagram and bending moment diagram. How we have drawn it? The shear force diagram was like this. Here it is WL by 2, sorry. WL by 2, and here it is WL by 2. This is the SFD. And remember this part. Yeah, this part, this SFD and BMD we have drawn.
Yes sir.
So this is the maximum bending moment. How it is known? That we also told that time that when the shear force becomes 0 about any section, the bending moments becomes maximum. And in this case, we are using the maximum bending moment only because that is directly connected with the maximum stress generated. So from this bending moment part, we are only interested to the maximum bending moment value. So this gives the maximum bending moment. This W square by 8 is giving us the maximum bending moment. So that's why the value or the expression WL square by 8 is our important expression. So we are just using that part only, WL square by 8, because जब हम लोग एक beam design करते, so there are other bending moments are happening, right? But the maximum is always is the most botherable thing. So all the engineers only bother with the maximum value. Okay. So maximum value is W square by 8. So that is coming from this part.
Excuse me,
And-
sir.
Yes.
सर हमारी फिजिक्स की क्लास है अभी.
हाँ पता है मुझे, बट वही मतलब पता है मुझे, वो पूछा ना इसीलिए मैं एक्सप्लेन कर रहा था. Okay, okay. So have you understood? If you don't,
Yes,
you can
yes.
check. Okay.
Yes sir, I understood.
Okay, okay. So I know you have class because I have seen the. Just 1 minute, okay? I am sharing that and